Hello, everybody. Well, congratulations. We've made it to the Friday before spring break. So, we're going to continue today talking about molecular shapes and how do we create a model of molecular structure, a three-dimensional model. Before we do that, however, I thought we'd have a quick discussion on the COVID virus and what are scientists doing to combat this virus. Well, what they're doing is they're trying to figure out the molecular shape, the three-dimensional shape of the COVID virus, so they can use this information to determine how it infects human cells. So here's some recent research that I got off the internet. And so here is a drawing of a coronavirus. And the specific type of coronavirus that we're concerned about is called COVID-19. So you can see that it's a spherical object and it has these little tiny spikes on it, all over it. Well, these spikes are extremely sticky and they can latch onto a human cell. So let's look at what the scientists are doing. So scientists exploring, the scientists who are doing this, how the coronavirus like COVID-19 infect human cells have shown that the SARS CoV2 spike S glycoprotein binds to the cell membrane protein antigen converting enzyme to ACE2 to enter human cells. COVID-19 has been shown to bind to ACE2, so that's the human cell has this protein called ACE2 on the outer surface that the COVID-19 uses to enter the cell. ACE2 via the S protein on its surface. During infection, the S protein is cleaved or separated into subunits S1 and S2. S1 contains a receptor. It's like a doorway. It contains a receptor binding domain. It's like the key to a door, a lock to a door, the receptor binding domain, which allows coronavirus to directly bind to the peptide base domain, PD, of ACE2. S2 then likely plays a role in the membrane fusion, in the ability of the COVID virus to fuse to the membrane of the cell. So here's another model of the ACE2, the ACE2 receptor complex that is on the cell membrane. The overall structure of the RBD ACE2 BOAT1 complex. And you can see how complex it is and how accurately the modeling has in looking at this molecular structure, this particular part of the cell membrane that is key to the ability of the COVID virus to cleave to the cell membrane and infect the cell. So what's the conclusion of this particular research that was done? Well, researchers have concluded that their research could contribute to the structure-based designs of decoy ligands or antibodies able to specifically target ACE2 or coronavirus spike proteins to prevent viral infection. So again, all of this work is based on determining the structure of molecular objects at the atomic level, at the molecular level. So fascinating. And that is why we want to determine molecular shapes. All of this work that scientists are doing to design a vaccine is based on their ability to determine the three-dimensional shape of molecules. So why don't we do a couple of these and then we'll end the video. Okay, why don't we start here where we left off? So here we have S, sulfur, attached to 2 chlorines. So I'm going to write the formulas over here. Sulfur dichloride. Chloride. Okay, so sulfur, if we go to the periodic table real quick, sulfur, there it is right there. It's in column 16. And chlorine, it's right there. It's in column 17. So sulfur has 16 minus 10 is 6 valence electrons. Chlorine has 17 minus 10 is 7 valence electrons. But I have to multiply by 2 because there's 2 of them in the molecule. So that's 14 plus 6 is 20 electrons. Okay, so I'm going to guess the structure using single bonds. I'll write sulfur in the middle since it's the first atom in the formula. How about if I put a chlorine over here and a chlorine over here? Okay, the act of making 2 single bonds, that's 4 electrons. We've just used up 4 electrons. So let's subtract 4, and I've got 16 left. 16 electrons, I'm going to populate the ligands or the outer atoms in the structure first. This chlorine has 2, it needs 6 more. 1, 2, 3, 4, 5, 6. And then this chlorine needs 6 more. 1, 2, 3, 4, 5, 6. Okay, so you've just used up 12. 16 minus 12 is 4. Notice this sulfur in the center. It's still only got 4 from the 2 single bonds, so it needs 4 more. And guess what? We have 4 electrons left. There is the structure, the 2-dimensional Lewis structure. Okay, now we look at this central sulfur here and we count the places that we find electrons. Well, we've got 2 lone pairs. That's 1, 2. We find lone pairs on the top and on the bottom. That's 2 places. And then we find electrons in 2 single bonds. So that's a total of 4 places. Then we go to our VSEPR table. Let's find it here. There it is. Okay, so there's 4 places where we find electrons. These are our choices right there. Of those 4 places, how many are bonding and how many are not bonding? Well, there's 2 single bonds and there's 2 lone pairs. So this is the structure. It's a bent structure. And here's a model, very similar to H2O. So let's go back to our, we know that it's bent. And I'm going to draw it like this. We've got an S in the middle. We've got a chlorine down there and a chlorine down there. And then we've got 2 lone pairs. And then this angle here is roughly about 109 degrees. And these lone pairs, they got little electron clouds coming out the top where those electrons hang out. Let's try one more. Let's try one more. How about ozone? Ozone. Okay, ozone. We have oxygen, which is 6 valence electrons, but we have to multiply that by 3 equals 18 valence electrons. Okay, so ozone, this is called ozone. And it turns out that ozone is a pollutant that primarily is the result of automobiles, driving automobiles. It's a pollutant. It's very stringent gas. I mean, you can breathe ozone, but it's like you're breathing an acid. It dries out your membranes. It's a pretty nasty gas. You don't want it around, but it turns out that there's a lot of it in big cities because we drive a lot of cars. Another thing that ozone does, if it's in the atmosphere, in the mesosphere, high in the atmosphere, about 20,000 feet in the air, well, more than that, it's about 80,000 feet in the air, the mesozone, and you have what's called the ozone layer. And an ozone layer in the atmosphere of the Earth, it blankets the Earth and it protects us from the ultraviolet rays of the sun. If we didn't have an ozone layer, there would be no life on Earth because the harmful rays of the sun would hit the ground, and anything that it receives a lot of these rays, it can't live. It dies because of the ozone, the harmful rays of the sun, like UV radiation. They interfere with organic life. That's one reason why we use a lot of sunscreen during the summer. Okay, so let's figure out the structure. I'm going to put an oxygen in the center. I'll put an oxygen on this over here, and I'll put an oxygen over here. I like to put things symmetrical if I can. So I'll put two oxygens on opposite side of the central atom. So how many electrons have we used up? 18. We've used up 4. That's, what is that? That's 14 left. Okay, I'll populate the outer atoms first of oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used up 12. 14 minus 12 equals 2. I've got 2 left. 1, 2. Now notice this central oxygen, it only has 6 valence electrons. It's got 4 from the 2 single bonds, and then it's got a lone pair. So that's not enough. It needs 2 more. So to give it 2 more, I'm going to take 2 of these electrons, and it doesn't matter which ones you take. I'll take those, and I'm going to bring them down, and I'm going to make a double bond. So I'm going to get rid of these electrons right here. There we go. Okay, so there's the structure. So around this central atom, notice that there's 1 single bond, there's a lone pair, and there's a double bond. So that's 3 places where we've placed electrons. What is the shape? Well, we go to our shape, the VSEPR table. We look at the number 3. Here we are. Here are the choices. There's 3 places where the electrons hang out. 2 of the places are bonding. We have a single and a double bond, and 1 place is a lone pair. So again, notice that this is a bent structure. So I'm going to say it's bent. We got an oxygen on the top with a lone pair, then we got an oxygen down there and an oxygen down there. Notice that the oxygen or the ozone, you can draw it 2 ways. You can draw it with a double bond on the right, or you can draw it with the double bond on the left. So you have 2 choices. You know, these are different oxygens on the outside. There are 2 different oxygens. We have a right oxygen and a left oxygen. You have 2 choices. So when there are more than 1 choice, we call this situation resonance. Resonance. And what that means is that these structures, they flip back and forth. They flip back and forth between these 2. And in fact, what ultimately happens is that the structure of ozone is really looks something like this, where the double bond kind of spreads itself over the whole molecule. So you have 1.5 bonds between the atoms in the molecule. And we indicate that by a dashed line. Okay, so that's it for today. I hope you have a good weekend and a good spring break. Bye-bye, everybody.